Welcome to the world of data center innovation with the iMasons podcast, discovering the people leading our industry revolution. My name is Romain Tranchant, and today I'm joined by Jon Summers, scientific lead in data centers at RISE, the research institutes of Sweden. Jon has agreed to talk to us about the different liquid cooling technologies available, their performance, and typical use cases. Let's get right into it. Hi, Jon. How are you?
Hi, Roman. Yeah, very good. Yeah, how are you?
Yeah, very good. Thanks very much for coming on the podcast today. Second time's the charm.
Thanks a lot for inviting me back. Yeah.
Yeah, well, we had a great discussion last time, and I'm pretty sure it's going to go exactly the same way today. This is part of a series that we've been preparing in the background, following a survey we've done last year on liquid cooling. One of the things we found out is liquid cooling is a different things to different people. So we thought we'd invite you back in, pick up your brain on what it is, the different performances, the different types, maybe some of the nitty-gritty for our more geeky colleagues out there who wants to know a bit more. But before we go into this, let's go through air cooling, because you and I had an interesting discussion on the fact that it's not away yet, and we could push the performance of air cooling quite far if we wanted to. Can you take us through this?
Well, I think, obviously liquid cooling and data centers, liquid cooling things with liquids is quite a common thing. And we can talk about some of the historical aspects of this. But I think with data centers, obviously air cooling has a lot of simplicity about it. And so, we do want to push the limits of that. And I have seen some applications where you increase the size of the heat spreader. So, you're generating heat and you've got to spread it out over a large surface area so that you use air which is a very low density fluid to pick up the heat and carry it away. So, and of course, the faster you move that air, the more thermal power removal you can deal with. So it's the rate at which the heat is generated and the rate at which the heat is carried away basically you can go on quite a long time if you're willing to accept large heat sinks, large heat spreaders in your data center, and you are willing to have massive fans blowing gale force winds in your data center. You can still do it, but the question is would you do that? And obviously, I think there are some interesting applications where you would really force the air at tremendous high speeds. We did a project a couple of years ago where we did have about 60 kilowatts in a rack of ASIC miners, and we were able to cool them with air, and so it can be done. So it's but there are challenges. There are challenges for standard data centers, going forward. Yeah.
So. Well, and clearly one point to pick up that we were told by Duncan on a previous episode is that everything is getting smaller, more condensed, because our computational needs are ever increasing or exponentially increasing. So therefore, bigger hit sinks is probably going against what we're trying to achieve. So if air is not the answer, where are we going from there? And I guess for anybody who listen, who's read the title, I guess they know where we're going with this, right?
Yeah, as I said, the density of liquids versus gases like air, for example, that helps us pick up a lot more heat with smaller volumes of the fluid. And so, you can do things at lower speed. You can also use some certain properties of the coolant to enhance that heat transfer. We're all about heat transfer, and this is a branch of mechanical engineering, because we're putting, if you think about it, these microprocessors that are very small, you're pushing in like 2,000 amps of current, and it's not going anywhere. It's just going straight in there. So you're not. It's unsurprising that we're getting really dense heat fluxes, sources of heat per unit area, if you like, which is what we call a heat flux. And so it's challenging to get that heat away. And that's why, as it enters that small microprocessor, what you do is you try to spread it out with a heat spreader, or you put something in contact with it now that can carry a liquid, and that's where the whole idea of liquid cooling. And I think, back to your comment earlier on where we said, there are various definitions of liquid cooling. Well, everybody has a different definition in their mind, what they think liquid cooling is. But I would probably say that for the purposes of data centers, where we've always had this siloed approach, there's the facility, there's the IT. Now, when the facility, which is all the cooling infrastructure, invades the IT in the way it does with liquid cooling, then that's what we really mean by liquid cooling in terms of data centers. So, pipes are going into IT, or IT is immersed in a coolant that is a dielectric, which we will come on to a bit later to talk about the different variations of liquid cooling. But it muddies the water. Who's responsible then for the coolants that go into the IT? Because the guy who's in charge of the server, pulling it out and changing a DIMM or something, he's now got to deal with the water pipes or coolant pipes, and when you disconnect these things, it can have a knock-on effect on the distribution. I mean, ideally, we're developing this now to be a much more mature technology than it has been in the past. So all of these things should work just as smoothly as they have done in the past with air. Yeah, that's the plan. Yeah,
there is a couple of things that I'd like to come back on. Right, the first thing is liquid cooling is not new, and liquid has been slowly but surely invading the IT space, going from the crack unit alongside the walls to in-row coolers, rear door exchangers, and now being straight in the servers. Right, so it's been. So first of all, and we'll come back onto that in separate parts, but the first one is liquid cooling is not new. I do remember 1990s, late 90s, any gamer worth their salt would have a liquid cooling loop on their machines, right? So it's interesting that this is one of the technologies that have been first adopted in these types of mainly in the homes first, with all the disastrous consequences we know about leakage. And then, but there's now been revived through and at scale through data centers, right?
Yeah. I mean, I think, you're right. I mean, the reason we have a raised floor in a data center, not every data center has a raised floor. I mean, there's a move towards slab floors now, but that original concept of a raised floor was not just to pump air under the floor to cool the IT. It was there to allow your water pipes to go to your old IBM system that was liquid cooled in the 50s. So so it just happened to be, from a history perspective, I think it happened to be repurposed for downflow crack units and say, oh, we got a raised floor, so let's push the air under the floor to where we want it inside the data center. But you're right, for years we've been using liquids in and around data centers, whether they're in the crack units, liquids are there, the refrigerants are used, all the refrigerants are used in the chillers or whatever, there's always liquids. It's just that the liquids are probably mainly stopped at the edge of the data center, the white space where the IT is. But then, of course, I think with some of the supercomputers that came out in the early 2000s, we realized that we needed to enhance the cooling performance by adding rear door heat exchangers. So basically, this is a heat exchanger at the back of all the servers that captures the heat coming out of the back of the servers by air. It's still the main transport is the first part of the transport. The heat transport is by air, but then it hits a heat exchanger, an air to liquid heat exchanger, and liquids are passing through this heat exchanger and extracting that heat from the air. So the computer room air conditioning units or the computer room air handling units had less heat to deal with, because we managed to get quite a bit of the heat from the rear door into the facility water network, because the rear doors are actually close to the IT. So the next stage really is to then say, well, let's get the liquids going into the IT, and then things start to get a little bit more crazy, if you like, or a little bit more interesting.
So we're now putting liquids directly inside the servers in different form factors, actually, and mostly people will know direct to the chip or literally immersions. Can you paint a picture as to the different, or what you would consider the different technologies for liquid cooling?
Yeah, and okay, yeah. So the direct to chip, I mean, going back to your comment earlier on about the gaming workstation, would have used a direct to chip with a small heat exchanger on the outside. So there would have been a water loop that goes through to a direct to chip, and a lot of the companies, or a few of the companies that are now making the heads and the cooling distribution for the rack for servers in data centers started off in that domain. That's where they came from. They started doing it in gaming, or on the guys that overclock their microprocessors and couldn't use air cooling to get rid of the heat, so they put a cold plate on there which allowed liquid to pass through it. So that's the direct to chip, which I think has been around for a long time and has established itself for supercomputers, if you like, the high performance computers. A lot of them use this kind of approach. But of course, when you've got a rack of servers, you then have to have quite a lot of pipe work. So you have usually what's called a manifold or a plenum, which carries your cold supply, and it's got a lot of tee-offs, which then provides a connection point to your hot components inside your server. And then there's another one which is collecting the heat the other side, and connecting that to the hot water side. It usually goes to what's called a coolant distribution unit. So there's a lower volume of coolant, of liquid coolant in that loop.
Right.
And then it's exchanged with the facility loop, which is carrying a lot more volume of liquid. Yeah. And so the direct to chip, very familiar in a sense from the supercomputing world, and the reason why it became so necessary in supercomputers was because a lot of the applications that we were running on supercomputers were, scientific calculations, required a lot of compute as close together as we could possibly get it. So it's because if your compute is far apart, then when you're doing your calculation, this transport time of data between two nodes or two aspects of the supercomputer will slow down the calculation. So we want to bring it all close together. And now, that same requirement for AI data centers has appeared, because, you want a lot of the GPUs that we talk about that are used, sometimes called accelerators, if you like, used in AI training. We want them as close together as we possibly can. So you don't want massive heat sinks. So get rid of those massive heat sinks, put in these smaller cold plates, and then pass a liquid through it. But then you have the problem is that a lot of compute these days has a lot of peripherals. It'll have memory, quite a lot of memory. So supercomputers use a lot of memory. And so that memory is quite energy intense as well, but it generates heat in the air because you don't put a cold plate on them. You can put a copper conduction point which goes to your liquid cooling loop, so you can try and extract the heat through conduction a little bit. But usually you are still passing air through the servers with cold plates. So, and about 75 to 80% of the heat in a server is captured by the water loop with the cold plate and the direct to chip system, and then the other 20 to 25% is vented into the room or passes through a rear door heat exchanger, which we talked about a little earlier,
Yep.
to capture that heat as well. And so the whole system gets rather complex because you have a lot of different, and these things might be operating at different temperatures. There are some neat engineering ways to deal with this going forward, but it makes your data center look very much the same as it has always looked. With the racks, the standard racks, you just see a lot of pipe work above maybe or under the floor if you've got a raised floor, depending where you put the actual connection points that connects your CDUs to your plenums, your manifolds, which is collecting the heat from all your hot components in your rack. But the other way to do this is basically to take the rack and say, well, let's tip the rack over on its side, with the servos pointing upward, and let's just pour a load of dielectric liquid in there. Obviously, it has to be sealed. Okay, I'm being a little bit facetious there with that. It's the tanks that are developed today have evolved over years of development from a number of the companies that develop these immersion tanks, and this is another way of doing it. So you immerse the entire electronics into a dielectric coolant. Now the difference here is particularly the type. The fluid properties, or should I say the liquid properties. Fluid is a general term which you can talk about gases and liquids. Liquids are usually dense and they flow, whereas a gas is a bit more, it's less dense. So what we have to consider here is that we rely heavily on convection and some of it is natural convection, although that's probably now with the intensity of the microprocessors that we're seeing, you now need to force the coolant past the heat spreaders for immersion. You still need to spread the heat, like you have a cold plate which you put on your microprocessor. Inside that cold plate, there's usually a way of spreading out the heat over a surface, either with little fins or microchannels, or you might actually use what's called jet impingement, where you force the coolant down onto the surface and it impinges it at high speed and spreads out in all different directions and carries the heat away. But all of these different techniques are actually used today to try and maximize the extraction of the heat. So,
because the overall thing is that we also are forced to reduce the overall temperature of those chipsets. So staying ahead of the curve as they become more and more powerful is really the name of the game here.
Yes, I mean this is what has been observed with some of the microprocessors, is that the temperature, what's called the T-case temperature. So a microprocessor is built up. First of all, you have your microelectronics, and then you have a dielectric around that microelectronics to protect it. And then you have what's called an integrated heat spreader over the top of that, which is a metal cap that goes over the top. So first of all, you've got a difficulty because you've got now a dielectric. Dielectrics, by their very nature, do not conduct electricity. They don't conduct heat so well. So already you've put a barrier into heat. But then at the top of that, which is the integrated heat spreader, is called the case temperature. And it's that from the people working outside of the microelectronics realm and thinking about the mechanical aspect, the thermodynamics aspect of this, they're looking at that temperature, and that has started to drop, or the requirements of that case temperature have started to drop, which means the temperature, the approach to temperature of your coolant has to then drop as well, because you need to maintain that case temperature, that top temperature, to below a certain value. And if you let it go too hot, then, well, the consequences usually is that your microprocessors may throttle. They say, oh, I'm too hot, I'm going to have to slow down.
Yeah.
You say, like in the gym, if you overheat in the gym on the thing, you have to slow down to cool down a bit. Yeah.
Well, it never happens to us.
Unless you had a liquid cooled suit on, then you probably could carry on much. You wouldn't be overheating. Yeah. But anyway, so yeah, so these different aspects obviously complicate when anybody looking from afar saying, "What's this? What is this liquid cooling of microelectronics for data centers?" And then you suddenly open the lid and you say, "Well, there's like 50 different companies providing different solutions. You know, what are these different solutions? What is it?" But it's a variation of a theme, which is one thing. But there are unique aspects of the different setups. So I mentioned, you know, those cold plates that would use micro channels, and those cold plates that maybe use micro fins to spread the heat, or jet impingement. There are ways of actually causing the coolant as it comes close to the microprocessor, but it's within the enclosure of the cold plate, not actually touching the microprocessor, but actually in the enclosure, that it changes phase. It goes from a liquid to a vapor. And what we have in this situation is we have what's called the latent heat of vaporization. So latent heat of vaporization basically says when a liquid needs to go from its liquid phase to its gas phase, in order to break that barrier, that energy barrier of changing phase, you need to put energy into the system, and that energy comes from the heat. So you use the heat to phase change, and because you've used that heat to phase change, you basically drop the temperature around it. So, and this is a neat way of combining liquid cooling with what we call, if you like, evaporative cooling, which is where we use water outside the building to spray or to wet the air in order to humidify, or so that the water evaporates in the air and it cools down the air. Very much like when you sweat, the water vapor on the water molecules that appear on the top of your hand, when the air comes past it, it evaporates it, and it's a cooling effect. Just lick your finger and blow on it. You can feel it's cool.
Yeah, of course.
And it's this is exactly the mechanics, or the thermomechanics, that's being adopted here to try to improve the heat transfer. And it's kind of, in the enclosure, we're kind of boiling the coolant. So we're boiling it, we're phase changing it by boiling it. But that boiling, it doesn't happen at 100 degrees centigrade as you would happen with water. It's happening at a much lower temperature, because we're using a different coolant, a different liquid, which can boil at 30 degrees centigrade or 35 degrees centigrade. And they are called, they're fluoroorganics. They're usually used in refrigeration systems. And this enhances the heat transfer capacity. So this is what's called your two-phase direct-to-chip, as opposed to single phase, where you do not phase change it. You would use a water, we call it a PG25. So it's got a bit of it's got glycol in it, propylene glycol at 25%, and water. And also you put inhibitors, and you also put in corrosion inhibitors, and you also put in biocide, because you don't want any biological growth, and you don't want the fact that you don't. So there's lots of things you have to do liquid cooling properly, you know. So it's but of course this is now part of the whole package. Whenever you adopt a liquid cooling solution now for a supercomputer or for an AI data center, these are the things that we're going to have to do in order to be able to get the compute as close together as possible. Now, maybe
So
I should say a little bit more about immersion cooling, but maybe you want to.
yeah, no, I mean, I just wanted to summarize because I mean, it's very interesting to listen to, the different aspects of it. So just to summarize, so we've talked about liquid to the chip, the single phase versus two phase, and the fact that it now goes directly on the chipset with those cold plates. We've talked about immersion, force versus natural convection. So natural convections, the liquid gets hot, so it typically rises to the top, pulling cold ones on top, versus force, which is really just a pump actually doing that effect to accelerate the amount of liquid that goes over the plate. And then again, within the immersion, you've got single and two phase as well.
Yes, I mean, two-phase immersion, I think, is a very big. I mean, it's a nice idea, but I think it has a lot of challenges, because one of the things. So within two-phase direct chip, it's a closed system.
Mm-hmm.
So the coolant phase changes. It basically boils, and then you go to your heat recovery unit, or your CDU, your coolant distribution unit, and you condense the liquid back to liquid phase by extracting the heat.
Mm-hmm.
But you basically trade temperature for pressure in that system. So every time you change a liquid, if you phase change from liquid to gas, the gas, it needs more space, if you like, so the pressure goes up. So you're trading the pressure there. But if you go for a tank solution, if you think about the coolant changing phase, you need to condense it.
Mm-hmm.
Or if you just had an open tank, you would lose it all. It would evaporate.
I see.
Completely.
I mean, we're running on empty after a few hours. Yeah, of course,
exactly. Yeah. I mean, if you get some of these liquids that are used and you put a cup of it in, and you put it on the side for 24 hours, those that boil at 35 degrees, say, and in room temperature, it'll all evaporate very quickly. It doesn't. So you need an enclosure. So with a two-phase immersion system, you need to maintain a tight enclosure. But of course, with that tight enclosure, you need to be able to get in some way of condensing the coolant, so that you change it back from gas to liquid, and it drops back into the tank. And then you need to bring in cables for power and data in and out. So it's very challenging to make it sealed tight. And because you need to use an engineered fluid to do this, you need to use a fluoroorganic. You can't do this. You can't do two-phase immersion yet with hydrocarbon. I don't think he will ever be able to do it with hydrocarbon, I don't think. But because it's a fluoroorganic, it's usually a hydrofluoroether or a hydrofluoroolefin or something like that, which are classified as PFAS. They come on the PFAS radar, and so, which is a forever chemical. Well, not all of them. I mean, this is a big subject, about whether, the different chemicals, because, obviously when Europe is coming along and with the REACH, what is it, the chemicals REACH, and saying, we should ban all these substances. They didn't realize, I guess when they were saying that, they didn't realize the incredible economic magnitude effect that would have on a lot of industries that are completely wedded to using these materials until they can find alternatives. So, but anyway, that's one of the aspects of two-phase immersion, which is why I think it's a big challenge. Whereas single-phase immersion, yes, some of the hydrocarbon does end up as vapor. You do get small molecules but you don't lose much of the coolant when you open the tank and close it, and it does depend on the viscosity of the coolant, because so you want a hydrocarbon which comes from Lubrizol, Valvoline, Castrol, Shell. All these guys are manufacturing these now can be used as an immersion coolant. You want it to flow easily with the pump. You don't want to put too much energy into the pump. You want it to go through the heat spreader. So you have to have a heat spreader as well. You need to spread the heat out. But you don't want it to evaporate, and so
Right.
so you have to play around with the properties of the coolant, and this is what these guys are doing. They're trying to get it so that it doesn't use so much pumping energy, so that it can carry the heat away relatively easy. And of course, we also know that hydrocarbons, as they heat up, their viscosity drops. They get more and more. They flow more easily at higher temperature than at lower temperature. It's a bit like honey, for example. As you heat it up, it flows much easier. Yeah.
So that leads me on to thinking. You've been using the word liquid, hydrocarbon, fluid. So this is one of the same thing, right? So there is only one type of liquid out of all of them. That's it. Simple game. Go to the corner shop, buy it, put it in, done, right?
Well, could be. I mean, I guess I use the word fluid as a generic term because it's when we talk about fluid mechanics, we talk about anything that can flow. So a gas can flow, a solid can flow as well. Glass actually flows, but it takes a long time. And there is a measure of how fast it flows. It's called the Deborah number, which is based on the book of Deborah and how the mountains flow in the book of Deborah in the Bible. Yeah. So we use a number that associates flow, but that's the generic name. Underneath that, we've got liquids, gases, solids, if you like solids. Some solids don't usually flow, but some flow over really long time scales. Mm-hmm. And then under the liquids, we've got the classification of the liquids, like the fluorocarbons. Well, they can be a gas as well because they can phase change. So depending on the temperature and pressure, they can be a gas or they can be a liquid. And the same for hydrocarbon. But hydrocarbons, I use that to mean like transformer oils, silicon oils, synthetic oils. Anything that is based on with the carbon and the hydrogen atom, hydrocarbons and oxygen, of course. Yeah. So I think, or maybe it doesn't have oxygen. My chemistry is not up to. But and the fluorocarbons, when I talk, it's carbon and fluorine atoms that appear in that, and these are two different types of liquids. When they're in their liquid state, they can be in a gas state as well, which depends on pressure and temperature. So that's the classification. Yeah. And so for an immersion system, yes, you can literally, if you want, take a load of servers out of the rack, throw away the fans, take off all the sticky labels, remove the thermal interface paste, and put something that doesn't flow, because that's between your heat sink and your microprocessor. There's usually a little bit of paste, which is designed to maximize the heat transfer from the microprocessor to the heat sink, the thing that's designed to spread the heat over a larger area. So once you do that, you throw the IT into the tank, you pour in the hydrocarbon, and off you go. Yeah, but so it's a lot more complicated than that, of course. Yeah.
And I can imagine, but just to confirm, so whoever is manufacturing, you mentioned a few brands earlier, whoever is manufacturing those liquids are playing around with the different parameters of all those liquids to figure out what the best is, right?
Yes, I mean their unique selling points will be, how the performance of the coolant for immersion, and it may also be material compatibility as well, because don't forget the coolant when you're immersing servers in a coolant, there are lots of different components on the server, that are made of different materials, and so that you don't want that to degrade in the coolant. So material compatibility is very important here. And so this is a big topic for immersion. One aspect of immersion is understanding, how the coolants interact with all of the material components that make up the servers and all of the other components. So, for example, the classic one is that your traditional cable, your network cable, or your power cord, usually have PVC in them. It's got plasticizer in it. And if it's in oil, if it's in a hydrocarbon for a long time, that leaches, that comes out of and the cables get brittle. So they would
right. Okay.
Yeah. Yep. So you need to use a particular type of material cable, or you've got to go to one of these coolant manufacturers who say that they have a coolant that doesn't do that. That works well with plasticizers, but that is a challenge. Yeah. So that's that's what's happening in that domain. Yeah. So you've got the coolant manufacturers that are working on that, to try and improve the performance, the material compatibility, the longevity, the environmental impact, etc. All these kind of things is being considered. Yeah.
So whilst we're going to have a full-blown podcast on the topic of the changes of the infrastructure because of liquid cooling, and we've been mentioning a fair few changes already. One of the ones that I wanted to come back on as a first step out of that first liquid cooling inside the rack. So you mentioned the CDU. Can you talk a bit more about its place within the infrastructure, what it does, why it's important, and maybe some of the characteristics of it?
Yeah, so I mean, one way to look at this is that, when we distribute power to all of the IT components within a data center, you've got massive power cords coming in, and then you split this out into a delivery system. It uses PDUs at some point, and the power distribution unit is basically a way of connecting the primary power to splitting up the power to every single component. And so a CDU does the same thing, but in the liquid domain. You're passing liquids through into an immersion tank. For example, in an immersion tank, you will have a heat exchanger, and on one side of that heat exchanger, you will have the hydrocarbon circulating the tank. And on the other side, you would want your facility water that is going out to your chiller or to your heat recovery unit. And so that component that has the heat exchanger, which is right next to your tank, can be classified as what's called a coolant distribution unit. In the rack situation, where you have manifolds and you have all these tap-off points that have little pipes that go into every single server to extract the heat from all of the hot components in that server, that then is connected to a heat exchanger, and that heat exchanger sits inside a CDU. And on the IT side, or if you like, the technical side, where all the coolant goes through all the IT, is one coolant, and then there's a heat exchanger. And on the other side of the heat exchanger is the facility cooling loop. Which goes out to your chiller or your heat recovery unit. So it's a way of dividing, primary coolant from secondary coolant. Well, you might have primary to secondary to tertiary. I mean, the rack might be tertiary; it might be the third one in the loop. So, but the problem you have with all this is that, you've got. I've talked about thermal interface material, where you lose temperature across that. Then you spread the heat, and then you lose temperature across that. Then you use a coolant to carry the heat around to a heat exchanger, and then across the heat exchanger you lose heat, and then you go across another heat exchanger, you lose heat. So if you're talking about recovering the heat, we need to close the gap on all of this, and that's where great engineering can be applied. Using different materials for the thermal interface materials. Much better design of heat exchangers, so that the heat exchangers, the gap of the temperature gap across the heat exchanger is better, and maintaining correct flow rates, so that you're recovering the heat at a good grade of heat, so you're not losing energy in the system as much as possible. But of course, well, and that can be an immersion tank which is the coolant moving around inside the immersion tank is the same as moving the coolant around the manifolds and through all the little pipes. It's the same thing. The CDU sits there and separates the IT side of things from the facility side of things. So yeah, go ahead, Roman. Yeah.
I was going to say, so we're this is all very new. Well, not very new usage at scale, right? So, and we talked about that at the introduction of the podcast. That whilst liquid cooling has been there for a while and has been probably a very niche applications to certain things that couldn't do any other way. Now that we're using it at scale, what are the directions of research or maybe the speed at which we're making the solutions evolve to meet with the new demands?
I think it's good to. I think everything we need to put together is out there. It's about bringing all the technologies together, because it's the way that you might pump the coolants to the CDU to a CDU from multiple racks, or how you might have multiple CDUs. Do you have CDUs at either end of the rack? I mean, some of these CDUs are quoted to deal with 2 megawatts of heat, of thermal power. So if you had 2 of those, one at each end, you could have literally 4 megawatts of thermal power in a row of racks, but of course that's not going to be uncommon with AI, with the 125 kilowatt racks that are already hitting the market now with the NVIDIA and was it the NVL 72, whatever it's called, when it does eventually become mainstream. But that's not the end of the story. The next generation of microprocessor will up that to 250 kilowatts in a rack, and then that will upgrade it, and then the next generation will push that to 500 kilowatts in the rack.
Yeah,
and then suddenly somebody will be rolling in 1 megawatt racks, and then I think. But at that point, I think something else would have happened. Somebody would have said, "Well, this is ridiculous. We keep trying to meet from the mechanical engineering and the electrical engineering side. We keep trying to meet the requirements of this crazy IT that keeps coming into our data center. Why don't those IT guys get together and sort this out so it doesn't require so much power?" But that's another story, isn't it? But at the moment,
it will be for another day. Yeah, absolutely.
Yes. We're on this trajectory at the moment where we can only see that that rack power for this type of application. I mean, it's not every. I don't want the viewer, your listeners to get worried here, because this is niche still. I mean, in a sense, AI workloads, although we see function of AI in sort of almost everything we do within the IT space. You can apply AI everywhere. It's going to hit a lot of the applications, but I don't think all data center infrastructure is going to require 1 megawatt racks. You wouldn't do it that way. You're still going to have the low density stuff, and you're still going to have the beautifully crisp air cooling systems that are so simple to operate and deal with. I mean, liquid cooling. I've been talking about liquid cooling for many, many years, and some of the listeners will probably remember me talking about it back in 2010, saying, liquid cooling is going to hit us one day. And I used to say liquid cooling is
closer than it used to. Yeah. It definitely feels a lot closer. That gives us a very nice segue onto a bit of a reveal on what's going to come next, because a big part of what you said is all the components are out there, but now is about figuring out how to put them all together. So we're going to have somebody specialized that has gone through the hands-on learning of immersion cooling. So we're gonna learn all about the barriers to adoptions, the issues, and all the stories that comes with it. So that's going to be fascinating as well. Just as a last point, so you mentioned that OCP was doing some great work on liquid cooling. Just a two-phrase thing on what they're doing and maybe where people can find it.
Well, well, what I would say, just a little bit of history on that. I mean, I think it was about 2018. I think in the regional summit, because OCP does this regional summit and then the global summit in the US, and I think because there was a lot of energy, if you like, going into liquid cooling solutions within Europe, it seemed like it was the place to talk about it at that time. And they set up these subgroups. So I think there's a subgroup that's looking at immersion, a subgroup that's looking at rear door heat exchangers, a subgroup that's looking at direct to chip. And that's on that opencompute.org website. You can just go to the sub-projects and you'll see, and you can go to the wiki of all of those sub-projects. And within the wiki, you will find a huge amount of valuable information. And I mean, the guys that that put a lot of time into this have done a really good job at bringing a lot of things together. And I think on the immersion side of things, there's a lot of information around some aspects of signal integrity. If you're immersing some things, what happens to the signal, because you don't want to. That's also something. Material compatibility, maintenance, and so because one of the things that we must be aware of is that I think you need to get into a routine maintenance cycle with liquid cooling that is very important, and that liquid cooling, the maintenance of liquid cooling, will require us to make sure that we don't allow any of the cooling paths to foul up in any way, whether it's because of corrosion or because of organic growth or whatever that's happening there. So there needs to be a good maintenance cycle. And I think that's where Open Compute has started to talk about these things in an open way. And there are a lot of the providers of the solutions, the liquid cooled solutions, whether it be immersion or direct to chip, are involved in Open Compute and talking about that. So it's a good source of material. I mean, it's vetted by a community, so it's not peer reviewed, but it's vetted by a community, and so it is a useful place to go to understand some of these more nuanced aspects of liquid cooling, if you like.
Jon, it has been once again a fascinating discussion with you on the various aspects of liquid cooling. Thank you very much for taking the time and sharing your experience on all this today. For those of the listeners that want to find a bit more about iMasons as well, I'm just going to put the website on the podcast. iMasons is really here to connect, grow, and give back. That's literally what we're trying to do, which is why we're making this podcast available to everybody. As we have connected and grown, we're giving back to the community that helps us so much on the day-to-day. If you want to reach out, you can reach out directly to myself, romain.truncheon@imasons.org. If you want to feature on the podcast, or there's topics that you want to listen to or hear about, please let us know. We can always organize something, and there is always a member in our community that is ready to step up and actually explain. In the meantime, once again, Jon, thank you very much for taking this time today, and we'll hope to see you again very soon on the podcast.
That's great. Yeah, and if anybody wants to reach out to me, please do so. I mean, I've only clipped the tip of the iceberg on all aspects of liquid cooling here. There's a lot to say, and I talk a lot. Yeah. But
this has been great, Jon. Thank you very much, and see you soon. Take care.
See you soon. Bye now. Thanks.
Bye.